In this video, we'll be going through the 2019 Electricity and Electromagnetism paper. Okay, question 1. We've got some sort of circuit for a lamp on a bike, and we can see that there are two resistors, a voltmeter across one of the resistors, a voltage source, and we're asked in the first question to show that the circuit current is 0.8 amps. We're given that the voltmeter reads 4, so the voltmeter here must read 4 volts, and this is a simple exercise in Ohm's law. Ohm's law tells us that V equals IR, where if we know the voltage across this here resistor and we know the resistance in this resistor, we can find the current in this resistor. And so if we solve this equation for current and plug in our numbers, we indeed get 0.8 amps. Calculate the heat energy dissipated in 2 minutes by the resistor marked R. And so if we look at our circuit above, well, since we know that this resistor here is using 4 volts, then this resistor here must be using 11 volts. And so the voltage across this resistor must be 11 volts. And we know the current in the circuit because we just found it here. So if we know the voltage in this resistor and we know the current through the resistor, we can find the power. Power is, of course, equal to current times voltage, and you'll find that on your formula sheet. Putting our numbers in gives us 8.8 watts. Now, a watt just so happens to be a joule per second. So if we multiply our power by the amount of seconds that we're dissipating our energy, we will get the total amount of energy dissipated in those amounts of seconds. So long story short, our energy is equal to our power times the duration in seconds. The power being 8.8, and the amount of seconds in 2 minutes being 120. Putting that in our calculator gives me 1056. Now, since the question has, for the most part, only given us 2 significant figures, I'm going to write this as 1100 joules. Another part of a circuit in the lamp is shown below. Calculate the total resistance of this circuit. So if we look at this top branch here, we see that we have 2 resistors in series with each other. And since they're in series, the resistance of this top branch is just going to be their resistances added together. Now, this top branch is, of course, in parallel with this resistor. And so the resistances in parallel add reciprocally. So our total resistance is going to be 1 over our top branch, which is 6 plus 5.6, plus 1 over our bottom branch, which is 3.2. Now, to rearrange that to solve for RT, we just need to flip both sides. Which gives me 2.5081. So I'm going to round that to 2 significant figures because that's what the question has given us, which gives me 2.5 with units of ohms. Jason's friend Deborah designed the following lighting circuits, and Jason wonders which circuit would give out the most light. All lamps are identical, but circuit 2 has an extra lamp. By considering the combined brightness of all lamps in the circuit, give a comprehensive explanation comparing the total brightness of circuit 1 to circuit 2. So by total brightness, I'm assuming they mean the amount of light put out by all of the lamps. And the amount of light put out by all the lamps is going to be characterized by the power usage of the circuit. And so, as we looked at before, power takes into account both the current and the voltage. And so the voltage for each circuit remains the same. But by adding an extra lamp here, what we do is we're adding an extra pathway for the current to travel. And that extra pathway, in a sense, reduces congestion, if you want to think of it that way. And so we actually decrease the resistance by adding this extra lamp. Now, Ohm's law tells us V equals IR, where if our voltage remains the same, if we decrease our resistance, our current must increase. So our current in this circuit too must be increasing. So if the current increases and the voltage remains the same in our second current, then our power goes up, meaning that circuit 2 consumes more power and therefore has the most brightness. So let's try put that into words. Adding a bulb to circuit 2 reduces the overall resistance. Since V equals IR and the voltage is constant, the current must increase. The brightness of the circuit is described by power, where P equals IV. As the current increases in circuit 2, it must consume more power and therefore be brighter. Question 2. Manu thinks that he could use an electric field in space to slow down a rocket ship. He sets up a model with a pair of parallel plates 1.2 meters apart. He connects them to a 550 kilovolt supply and uses a small toy rocket as a trial. We're given the mass of the rocket. The rocket moves from left to right, as we can see in the diagram. And the charge on the rocket is 3.5 times 10 to the minus 6 coulombs. And we're asked to calculate the strength of the electric field between the plates. To do this, we can use the equation on your formula sheet that the electric field equals the voltage over the distance, where we have both, so we just need to put in the numbers. Now, note that kilo, of course, means 1,000, so you need to times the 550 by 1,000, which gives me 4.58333 times 10 to the power of 5. And since we're given two significant figures as a minimum in this question, I'm going to round that to two significant figures, which gives me 4.6 times 10 to the power of 5. And the units of electric field are volts per meter. During one test, the rocket was initially moving at speed v and was stopped in a distance d. Explain in depth what would happen to the stopping distance if the rocket was tested again at double the initial speed and the same charge. So this is essentially a conservation of energy question. The energies that we're concerned with are the kinetic energy of the ship, which is given by half mv squared, and the electric potential energy, which is given by EQD. And so I'm going to start my answer to this question with a little bit of algebra. If the mass, charge, and electric field are constant, doubling the velocity will quadruple the distance. This is due to the square relationship between v and d. Moving on. Draw the field lines between the two plates. So this is a pretty straightforward question. We're just going to have field lines going between the plates. Now, one of the linchpins of this question is going to be making sure the lines point in the right direction. And electric field lines always point towards negative. And since this is the negative side and this is the positive side, we know this because of the voltage source here, the field lines are going to point in this direction. The maximum stopping distance for the given setup is 1.2 meters. What is the maximum speed that a rocket can initially be moving and still be stopped by this apparatus? So this is essentially taking the relationship that we had to explore in, I think it was B, and making us plug numbers into that particular scenario. So we're once again looking at the energy transformation between kinetic energy and electric potential, where our kinetic energy is once again half mv squared, and our electric potential is EQD. And we just want to solve for the speed, knowing all the other things. So I believe we're given all these other things in the sections above. So let's jot those down now. Converting our mass into kilograms. And I think that's all we're going to need. So let's now solve this equation here for our velocity. I'm going to start by multiplying both sides by 2. Then I'm going to do a 2 and 1, as I like to do. I'm going to divide both sides by mass, and then I'm going to square root both sides. Now we just need to put in our numbers. Which gives me 5.4518. Because the question has given us two significant figures, I'm going to round that to two significant figures once again. So I'm going to write that as 5.5 meters per second. On to question 3. The magnetic North Pole is a point on Ellesmere Island in northern Canada. Blah, blah, blah. Magnetic field lines enter the ground vertically. Strength of the magnetic field there was measured to be 47.3 times 10 to the minus 6 Teslas. The bicycle has metal handlebars that are 42.0 centimeters wide. A student riding the bicycle on the island rides on flat ground at 13.5 meters per second. We're given a bit of a diagram there and a picture that we're unable to see. I'm just going to guess that we're looking at some sort of bicycle. This is my best drawing of a bicycle. So the handlebars are 42 centimeters wide. And we are asked to show that the voltage induced across the handlebars is 2.68 times 10 to the minus 4 volts. So let's first write what we have been given, converting the distance into meters. And so the equation that we are interested in here is voltage is equal to BVL, where I have already faux pas a little bit. I've called our distance D, where that is equivalently our length of our wire, if you like, in our field. And now all we need to do is just plug in our numbers. Which gives me 2.68 times 10 to the minus 4. Since we are, let's have a look. We're asked to show that it's 2.68. And we are given three significant figures as well. That's unusual. We're usually only given 2, so that's nice. So that's 2.68 times 10 to the minus 4 volts, which is fortunate because that's what we're trying to do. Give an in-depth explanation of how a voltage is induced across the ends of the handlebars. And so the handlebars are moving through this magnetic field, cutting across our field lines. And so when a wire, or in this case handlebars, a conductor, cuts across a magnetic field, cuts across the field lines, it is going to experience a induced voltage. And another part to the question that it may want us to point out is that the direction of the magnetic field, if you use your right-hand rule, your fingers will go into the page. You can't see my hand right now, but do it yourself. Fingers go into the page. The handlebars, or your thumb, point towards the right, and so the palm of your hand should be pointing upwards, indicating that positive charges are going to be forced upwards. Therefore, negative charges are going to be forced downwards. And so that's another point that they might want in the assessment schedule. So let's try and put that into some words. The handlebars cut across magnetic field lines, causing a voltage to be induced. Positive charges are forced upwards, negative charges are forced downwards. Question C. The student then rides up a steep hill at 13.5 meters per second. What is the effect of riding up this hill on the value of the induced voltage? We're asked to circle one. Now, this effect is at its maximum when the movement of the charges, the movement of the conductor, is at right angles. The more you become parallel to the field, basically when you are directly parallel, the effect goes to zero. So you find your maximum effect when you are perpendicular to the field lines, cutting across them in the most efficient way possible. And when you're completely parallel, you get no effect at all. Now, this is described sometimes at year 12 level as having a sine theta on the end of it, where the angle in question is this angle here. And so a thing you should hopefully know about sine theta is that it is at a minimum when theta equals 0. In fact, the sine theta goes to 0, and it's at a maximum when theta is equal to 90 degrees. And so this is really a mathematical expression of what I'm about to put into words. And so the voltage is in fact going to be less, and let's try and put this into words. Okay, Chrome just crapped its pants, so I lost all the writing that I just did, which was fine. I was only 3 words in, so let me just recircle that for continuity purposes, and let me try continue with my answer. The induced voltage is greatest when the velocity is perpendicular to the field lines. It is 0 if the velocity is parallel. As the bike velocity is now less perpendicular, the induced voltage will be less. The student has an after-school job at a junkyard where they're moving a 1.5 meter steel pipe through a 0.8 Tesla magnetic field of width 1.2 meters at right angles to the field. The ends of the pipe are connected to a circuit that is outside the magnetic field. The circuit has a resistance of 5 ohms. We are asked to calculate the force that the student needs to exert in order to keep the pipe moving at 3.1 meters per second at right angles to the field. Okay, this here is a bit of a doozy. So let's begin by writing down all the things that we are given. Now, the length that you want to use is explicitly the length of the pipe in the magnetic field. And so the length of the pipe in the magnetic field is this 1.2 meters. The fact that the pipe extends beyond the magnetic field is really of no consequence. It's not in a magnetic field, so it's not contributing to the effect. So don't fall into the trap of using the 1.5. Okay, Now, to find the force, we're going to need to use this equation on your formula sheet, which is that the force is equal to the magnetic field times the current times the length of the pipe in the magnetic field. Now, we know our magnetic field, we know our length, but we don't know our current. So to find current, we're going to need to use V equals IR. Solving that for current gives us current is equal to voltage divided by resistance. But we don't know the voltage, so we need to now find the voltage. The voltage can be given by this equation on your formula sheet, that the voltage for a length of wire moving in a magnetic field is given by B V L. And so we've really got three substitutions here. And so I could substitute it 3 times algebraically, but that can get a little bit messy, so I'm just going to calculate it 3 times. So let's put in our numbers, which gives me 2.976, and I'm going to round this to 2 significant figures, so that gives me 3.0 volts. Now putting our numbers into our current equation gives me 0.6 amps. And now finally putting all our numbers into our force equation gives me 0.576, which I'm going to round to 2 significant figures, so 0.58. And that's in newtons. So the crux of this question, then to kind of summarize what's going on, is that the pipe moving through the magnetic field is creating a voltage. The voltage which we found here. That voltage creates a current which is dictated by the resistance which we found here. So we found our current to be 0.6 amps. That current in the pipe creates a force that needs to be opposed. And that force that needs to be opposed is 0.58 newtons, which is the answer to our question. And that's it.